This is on BERT-based MRC QA models, where we'll be comparing BERT and DistilBERT. This is our contents. So first, I'll give an overview of what MRC QA is, which is Machine Reading Comprehension, question answering. Then I'll talk about the Squad 1.1 dataset, as well as the pre-trained BERT models, which are BERT and DistilBERT. After which, I'll compare the evaluation metrics like exact match, F1, training time, and then show a demo. So first, an overview of MRC QA. MRC QA involves answering questions based on a passage. So the passage is over here. Singapore separated from Malaysia, so on, 9th August 1965. And then when I give the question, which is when did Singapore become independent, what MRC QA is supposed to do is extract from the context the correct answer. So this is the MRC component, which involves understanding the context plus question. And then this is the QA component, which involves understanding the question and answering it. So more on the Squad 1.1 dataset. This is the Stanford question answering dataset, version 1.1, and it was gathered from Wikipedia. And based on about 500 plus articles, people managed to gather about 100,000 question answer pairs. So Squad 1.1 by itself is not sufficient for the MRC component, which is the Machine Reading Comprehension component of MRC QA. So it lacks sufficient data for that. So what we need is a pre-trained model, which is BERT or DistilBERT, and then you fine-tune that on Squad 1.1 for the question answer pairs. And so after doing all that, we'll compare both the BERT-based MRC QA model as well as the DistilBERT-based MRC QA model. So firstly, on the pre-trained BERT models, which is BERT and DistilBERT. So this is what BERT stands for, bidirectional transformers, and it's very useful for MRC. It is able to capture contextual understanding of words, and is trained on large corpora for masked language modeling, which is MLM, where you mask some words and then you predict them based on the surrounding context. It is also trained on next sentence prediction, where you predict if sentence B logically follows sentence A. So example, sentence A is, tigers are common here. And then sentence B is, they are orange with black stripes. So this logically flows. So based on these two objectives, BERT is trained. Afterwards, we add a QA predictive head to BERT, which is over here. And then the QA head predicts for each token the logic on whether it is the start of the answer and whether it is the end of the answer. So here's the correct answer. So this is the answer start logic, right? And this gives the highest score. So 9th marks the start of the answer. And for answer end logic, this gives the highest score. So 1965 marks the end of the answer. And based on that, the answer is extracted from the context accordingly, which is 9th August 1965. So looking specifically on BERT, its model architecture, the BERT MRC QA model has firstly the embedding and then the encoder. So this part forms the pre-trained BERT model. And then you add the QA head, which is the third component. So firstly, for the embedding layer, this turns each token into 768 dimension embeddings. So previously, they are one hot encoded, about 30,000 dimension. Then you change it into a dense vector, which is this smaller 768 dimension. So there are three parallel operations that happen at first. So firstly, for word embeddings, it turns the 30,000 plus dimension, which is the vocabulary side, one hot encoded token into a dense vector, which is 768 dimension. And the position embeddings, they encode the positional information in the sequence. So the sequence is firstly the question, followed by the context, and each token will have a position. And so this encodes all the information. Lastly is the token type embeddings, which denotes whether a token belongs to the question, example over here, as well as whether it belongs to the context instead, right? So this is how the sequence actually looks like. So you do a matrix addition ++ to get the full embeddings. And then you apply layer normalization over the hidden dimension per token. And then you do a dropout with a 10% dropout rate. So next, for the encoder, it has 12 stacked encoder blocks, as you can see over here. So for each encoder block, it uses multi-hit attention, a feed-forward network, and along the way, it adds residual connections and then does layer normalization here as well. So firstly, for the input to MHA, which is multi-hit attention, per example, per question answer example, this is the shape of the input, which is 384, which is the length of the sequence that we set, as well as the embedding dimension, 768. So MHA has 12 hits for BERT, and each hit converts the input into its relevant QKV matrices. So you can see that it downsizes the embedding dimension by dividing by 12 for each hit. So it's 64. And then you apply the scaled dot product self-attention to combine all these QKV matrices. So this is just running through Q times K transpose, normalized by this, which is the dimension of K square root, softmax row-wise, and then you multiply by matrix V to get this sort of matrix. So then you concatenate all the outputs for each hit along the embedding dimension. So it becomes 64 times 12, because 12 hits, back to the original 384 times 768. And then you do dropout, 10% dropout rate. And then you pass to a linear layer where there's no change in the dimension. So following which, you do a matrix addition with the residual connection over here, layer normalization, and then you drop out with a 10% dropout rate. So here are some of the details. After which, you pass it to the feed-forward network, in which the first linear layer will increase the hidden dimension to 3000 plus, and then you apply the GELU activation function, and then you decrease the embedding dimension back to 768 over here. So the GELU is used to add some non-linearity, and the increase in dimension over here, it helps it to capture more complex relationships. You can see it increase from 768 to 3000 plus. So GELU was used instead of the typical ReLU, firstly because the authors of BERT in the paper, they mentioned that they want to follow OpenAI's existing GPT at the time, as well as something more general in terms of GELU, is that it has a smoother activation at the 0 portion, so that helps it to capture more complex relationships. And then afterwards, you do the matrix addition with residual, layer normalization, dropout with a 10% dropout rate. So this is the same details as over here. And then you repeat that, the encoder block, 12 times. And then you pass to the, as mentioned before, the QA predictive hit, where you predict each of the logits for answer start and answer end for each token. So now talking on DistilBERT's model architecture, as well as its unique loss function. So the foundational DistilBERT, meaning we're not talking about the QA component, just the foundational model, it is trained using knowledge distillation. So this is the training process. So in knowledge distillation, we have a teacher model, which is the pre-trained BERT model, and then the student, which is DistilBERT. So we still use the same large corpora of data, but when training DistilBERT, we also add in the predictions from BERT. And DistilBERT uses this thing called triple loss, which is masked language modeling loss. So you can see that both DistilBERT and BERT both use this masked language modeling loss. DistilBERT doesn't use next sentence prediction loss, but it does use this additional distillation loss, as well as the cosine embedding loss. So we'll talk about each of these. So firstly, MLM, which is masked language modeling loss, it is used by both models, right? So just a sort of recap, MLM is just to mask some of the words, and then the model will predict what the masked words are based on the context. So this is just the formula for this. This is just cross entropy over the masked words. So you can read this sort of formula. So this is the vocab size, n is the number of masked words. So this is for the ground truth, and this is the predicted by the DistilBERT model, right? So you can just combine it using cross entropy. And for next sentence prediction loss, that is used by BERT, but the authors found that it's not as essential, so they did not use it for DistilBERT. So yeah, they found it's not critical for downstream tasks. So DistilBERT does not use this NSP loss. Distillation loss is one of the key knowledge distillation techniques for DistilBERT. So this is the third thing that we're talking about. Distillation loss uses pre-trained BERT's MLM predicted probabilities as the ground truth for cross entropy. So again, this is quite similar to what we saw before. So this is the vocab size, n is the number of masked words. And in this case, the so-called ground truth is the teacher predicted probabilities by pre-trained BERT. And the student probability is by DistilBERT as per normal. So you can see here, this is used to be the ground truth. This used to be the predicted probability by the model. So this is the distillation loss used by DistilBERT. So for distillation loss, they use this thing called softmax temperature to make the probability smoother during training. So we can see here, this is the regular softmax, right? And then we add this t, right? You just divide by t, and we set t to be greater than 1, right? So as mentioned before, during training, we set t to be greater than 1, and this leads to softer probabilities. So this helps to better show BERT's varying confidence. So like, for example, if BERT is 60% sure that this word is the correct answer, as compared to this other word, which is maybe 30% sure, right? So we want to show this sort of variation instead of having a very sharp, like, oh, maybe 5% versus 90%, right? So this is what it means by softer probabilities. So we set t to be greater than 1 to achieve this. And then after training DistilBERT, during inference time, then we set t back to 1, which is just regular softmax. So the last component is cosine embedding loss, which is another key knowledge distillation technique used by DistilBERT. So cosine embedding loss, it compares the difference in each token's final hidden state for DistilBERT versus BERT. So you can see here the training using masked language modeling. And this is DistilBERT, and this is the pre-trained BERT model. So we pass in the tokens, and then at the final layer, we compare each token's hidden state, right? And we use cosine distance as a loss function for this cosine embedding. So you can see this is the formulation, where n is the number of tokens. So in this case, it includes both the unmasked as well as the masked tokens, just everything. And this is the first hidden state by pre-trained BERT over here by the teacher. And then this is the hidden state by DistilBERT, which is the student over here. And this is the formulation, which is cosine distance. So DistilBERT uses a linear combination of all these three loss functions, which you can see over here. So the coefficients are not explicitly given in the official DistilBERT paper, but you can maybe find it in the GitHub code page. So this is more on the model architecture specifically. So DistilBERT does not use token type embeddings because it no longer uses this next sentence prediction. And for the encoder blocks, it reduces the number from 12 to 6. So in spite of reducing the encoder blocks, DistilBERT is still able to retain most of the performance thanks to knowledge distillation, which is you can see over here. So comparing the metrics, we are using exact match and F1 to compare the performance, and then we're using the training time, specifically on fine-tuning on squad 1.1. So exact match requires 100% match of the ground truth and prediction, and we calculate the percentage of exact matches. And then F1 allows for some sort of partial overlap. You can see the formula over here. This is for precision, right? Where we take the overlap over the total predicted tokens. And this is for recall, where we take the overlap over the total ground truth tokens. So the training time is specifically for fine-tuning the BERT or DistilBERT model for MRC QA, where we pass in the squad 1.1 dataset. So DistilBERT-based MRC QA model still retains quite a large performance in terms of compared to BERT, with a significant drop in training time. So you can see DistilBERT only has a small drop in performance, as you can see over here. But DistilBERT has a significant drop in training time, which you can see over here, 87% drop. So in short, DistilBERT's drop in training time is well worth the slight drop in performance, as you can see over here. So now I'll show a demo. Oh yeah, and I'll show that later. So this is for BERT-based. So let's see over here, right? This is a question. It's asking about how many programming languages. And we can get the answer, which is over here, 13, correct, right? So same thing, this is the DistilBERT-based model. Then we get the answer, 13, right? So both perform very well. And this is just a reference over here, which I'll show. So that is everything. So thank you for listening to this presentation.